Today we are going to see the molecular orbital theory of chemical bonding. What we have seen before is the valence bond method of chemical bonding. So, that valence bond method also a quantum mechanical method. We are going to see another quantum mechanical method called molecular orbital bonding method. In this method, in valence bond method, we have a pair of electron needed for forming a bond. That pair of electron can be 1, 2, 3 like that, but the electron should be as pairs only, not as a one electron. The valence bond theory does not talk about bonding formed by using one electrons. We will see the difference while discussing about the molecular orbital theory. So, those pairs, shared electron pairs are located between atoms as far as in valence bond theory method is concerned, and it is mutually shared between the atoms. In molecular orbital theory, we will see that we have molecular orbitals. So, as you know or are very familiar with, if you take a hydrogen atom, okay, there is a nucleus and one electron is there outside. So, this is one-to-one interaction. For that, a Schrodinger equation was solved exactly and we got energy levels. So, you got s orbital, p orbital, d orbital, f orbital. So, these orbitals are nothing but wave functions or mathematical functions, because in wave mechanics electrons is treated as a wave. So, after that this Schrodinger equation Schrodinger equation for this hydrogen atom, that for hydrogen atom was solved exactly and we found energy levels and the orbitals s, p, d orbital. In the same way you can go for molecules. So, when you go for a hydrogen to helium, okay, so you have a nucleus, and then two electrons are here, one electron. So, this is one electron, this is another electron. So, this electron is attracted by this nucleus, this electron is attracted by this nucleus, as well as there is a repulsion between the two electrons. So, it is a three body problems which cannot be solved exactly. So, that is why we went for approximate method. Same way for calculating energy levels for molecules, we can adopt similar way, but the problem is the number of interaction is very high. So, solving the equation, Schrodinger equation for molecules is cannot be solved exactly. Solving the problem is very difficult. We cannot find a exact solution. Then we must go for a approximate solutions, because you can also do. So, if you follow the same way as here, when you build up the electron atom, higher atoms, you are adding proton to the nucleus and electron to the outermost orbitals. So, that way you can build up atoms. The same way you can build up molecules by fixing the nucleus. For example, nucleus A and nucleus B, as in the molecules, some molecules, AB molecule, and then you have to add electron to the energy levels, that is molecular orbitals, okay, orbitals formed by molecules. Okay. So, that is called molecular orbital. You can add electron to the molecular orbital and then you can calculate energy levels, but doing that calculation is very tedious and cannot be solved exactly. That is why we have to go for a approximate method of finding the energy levels. One of the approximate method is called a linear combination of atomic orbitals. So, it is LCAO method. Okay. Let us see what is a basic what is the basic logic behind this method for finding out the energy levels in molecules. Let us see an example. Let us see a molecule of this type H2 plus. So, you have a hydrogen atom and another hydrogen atom. Let us say this is hydrogen atom A, this is hydrogen atom B. Between them there is 1 electrons. Now, in wave mechanics, atomic orbitals, these are the atomic orbitals which are described by wave equations. Okay. So, if you take this hydrogen atom, okay, it can be described, atomic orbital of this hydrogen atom can be described by a wave function phi A, and atomic orbital of this hydrogen atom can be described by a wave function phi B. Now, so you have a molecule, this is a prototype homonuclear diatomic molecule, a very simple molecule. So, 2 nucleus 1 electrons. So, you can have that is the 2 nucleus 1 electrons. Okay. So, you have the electron here, the nucleus. So, it can attract here, this electron can be attracted here, and there can be repulsion between. So, it is a 3 body interaction. Okay, the equations, Schrodinger equation for this type of interaction cannot be solved exactly. So, that is the reason we have to we must go for a approximate method, such that will be very close to the exact values. So, what is that approximate method is the linear combination of atomic orbital. The basic idea behind this linear combination of atomic orbital can be explained using this prototype molecule. So, you have 2 hydrogen atom A and hydrogen atom B, and there is 1 electron. That electron at any time can be closer to this hydrogen atom. Okay. Then you can describe the electron or the whole molecule by using wave function of this hydrogen atom. So, this can be described by wave function of hydrogen atom A. If you have at another time, you can have that electron very close to this hydrogen atom. Then the behavior of this electron can be described by using wave function of hydrogen atom B. Now, if you have this electron somewhere in between these 2 hydrogen atom, Ha, you have Hb, and somewhere in between this hydrogen atom, then this situation, okay, about this molecule can be described by using by combining both orbitals, that is phi A and phi B. So, psi phi A plus or minus phi B. So, by combining them or combining the wave function of atomic orbital of hydrogen atom A and atomic orbital of hydrogen atom B, okay, you can describe the situation where the electron is residing somewhere between these 2 atoms. So, this type of algebraic sum, okay, phi A plus or minus phi B is called linear combination of atomic orbitals. So, you have 2 equations you can write. So, one equation is you just simply add phi A plus phi B. In another case, you can subtract wave equations, phi A minus phi B. So, that is called a linear combination. So, linear combination of 2 wave function gives 2 equations. In one case, 2 wave functions are added, in another case wave functions are subtracted. So, this is called, so this combination of this one is represented by a wave function psi, okay, equal to phi A plus phi B. So, this is atomic wave function of the hydrogen atom A, this is atomic wave function of hydrogen atom B. Combination is represented by psi, P S I, psi. So, this is called phi, this is called phi. Okay. Now, this one is represented by another psi equal to phi A minus phi B. Now, this situation, So, because okay, so another important parameter to be added is the normalization constant. What is normalization constant? That you might have studied while while discussing or while you studied about the atomic structures. So, that you will be studying more in higher classes. Now, let us take it as normalization constant. These are the normalization constant n added to the wave function, because we are starting with the approximate wave functions. So, to find the what is the exact energy, we are starting with approximate equation. So, we have to add a constant that is called normalization constant, so that finding the electron is positive. Probability of finding the electron is 1 somewhere, it should be somewhere. So, that is why we are adding a normalization constant. That right now you do not have to worry about this one. We can write the wave equation without this normalization constant. Now, we have to understand these two equations. You have psi equal to phi a plus phi b, and then you have another situation, psi equal to phi a minus phi b. What is the meaning of these two equations? So, we call this, when these two wave functions are added, it is called bonding B. When these two wave functions are subtracted, it is called anti-bonding psi a, this is psi b. What is the meaning of these two equations? That we have to understand clearly. Then only you can understand why one energy level is lower, why one energy level is higher in energy. Now, you have studied for hydrogen atom, the probability function for electrons is looks like that. Suppose this is a hydrogen atom, okay, hydrogen atom A, and its probability density function is given like that. Okay, so, this is a probability density function. Now, you have atom A. Similarly, that atom A is approached by atom B, and it also has the same electron density, probability density function. So, this is a atom B. Okay. When they combine, when they approach each other, okay, there are two possible ways. Because electron is treated as a wave, the wave has both positive and negative regions. So, when you combine two waves, there is a possibility for forming constructive interference as well as for destructive interference. What is that? So, if you take a wave, so this is a wave, this is a wave, this is one wave. You take another wave like that, then the resulting wave could be like that. So, yeah, so this is one wave, this is another wave, they added up, and then the resultant wave is having higher amplitude. So, this is a resultant, this is a resultant wave. So, this is called constructive interference. Suppose if you take a wave of this type, and then you have a wave of this type, and then resultant wave 1 is, it will be like this. So, this is the resultant one. So, same way, this is a one wave function describing atom A, hydrogen atom A, this is another wave function describing another atom B. When they combine, they can interfere, okay, they can interfere constructively as well as destructively. So, you can write, that is why, okay, so phi A plus phi B as well as phi A minus phi B. So, when they construct, when they interfere constructively, then it looks like this. So, this is the internuclear axis, here is the atom A, here is the hydrogen atom B. Okay, this is the nucleus and this is the internuclear axis. Okay. So, this is okay, the one way of describing the situation. In another case, you will have like this. You will have like this. So, this is a atom A, this is atom B. So, this one represent a buildup of electron density between two nuclei. So, this is a electron density. As you have seen before, if you take here atom A, you have a buildup of electron density. This is a buildup of electron density. Buildup of electron is maximum here, but there are so much electron density here. So, that is around the atom A. Similarly, you have electron density around atom B, which is represented in this way. So, when these two are combined, you can have like this. Okay. So, that is this in atom A, atom B, and between them so much electron density. So, this is from here so much electron density between. On the other hand, if they for this type of situation, in this situation, they can combine destructively as well. So, that the resultant one is like this one. Here nucleus A, nucleus B, and in between them, so there is a reduction in electron density. So, this one represent a reduction in electron density. So, here there is a increase in electron density. That in other words, the wave function of atom A and wave function of atom B reinforce each other, that is they strengthen each other between them. As a result, there is a buildup of electron density between them. So, what will happen if there is a buildup of electron density? So, that means the electrons are attracted by this nucleus. Similarly, electrons here are attracted by this nucleus. Here in between you have a mixture of electrons, the electrons from this nucleus, from this atom, electron from this nucleus. In other words, as well, that electron of this atom is attracted by nucleus of this atom, and vice versa, that is electron of this atom is attracted by the nucleus of this atom. So, that can happen if there is a buildup of electron density between two hydrogen atoms. So, that is represented by this type of graph. So, when there is a reduction in electron density, there is so you can have there is one electron density and then you have a electron density 0, here electron density 0, and then there is a increased electron density here. So, you can see here between nucleus A and B, there is a reduction in electron density. That means, if there is a electron density between two nuclei, then the nuclei are shielded and they are protected by the electrons. When there is no electron density between them, they repel each other. Actually, electron density is on other side. So, behind this there is some electron density. Similarly, after this nucleus there is a electron density. So, these electron densities are not mutually attracted. So, as a result, there is a repulsion between the two nuclei here, but here the atoms are attracted to each other. That is what this situation is represented by this equation. So, this situation is described by this equation. Is it clear? So, when there is a mutual attraction, energy of this system is lowered energy. So, that is called bonding situation. When there is a repulsion between the nuclei, energy is higher. So, that situation is represented by anti-bonding. So, this is bonding situation, this is anti-bonding situation, Wave functions reinforce each other. Wave function psi A and psi phi B reinforce each other. Here phi A and phi B cancel each other. As a result, there is a reduction in electron density between the two nuclei. So, this situation is bonding, this is anti-bonding, and here the electrons are attracted mutually. Here electrons are not attracted mutually, that is why higher energy. So, this is lower in energy, this is higher in energy. So, you could it becomes clear now that what is the meaning of these two equations. These two equations still one can represent these two equations in a diagram like this. So, you have a atom A, okay, hydrogen atom A interacting with another hydrogen atom B, and then there is one energy level lower in energy, another energy level higher in energy. This energy level, okay, or the result of interaction between the two hydrogen atoms. So, this one is phi A plus phi B, this one is phi A minus phi B. So, this is a bonding, this is bonding. Okay. So, hydrogen atom you have 1s orbital, which are singly occupied. Here there is one electron, there is one electron which are given here. So, this is atomic orbitals, okay, are combined to give molecular orbitals. So, this is called molecular orbitals. Bonding molecular orbital, you can say that, bonding molecular orbital. So, this one is called anti-bonding molecular orbital, okay, simply MO orbital, you can write it like that is higher energy compared to this one. Now, you can see here two atomic orbitals are combined to give two molecular orbitals. One is lower energy, another one is higher in energy. Okay. So, this situation, okay. So, with this lower in energy is described by this wave function, combination of wave function. Higher energy orbital is described by this type of combination of atomic orbitals. Now, if you take a, okay, so if you take a hydrogen molecule itself, so you have hydrogen A, hydrogen, then here it is a hydrogen molecule. Then these two electrons will occupy the lowest energy level. So, it will both will go to this lower energy state. So, lower energy molecular orbital energy level, molecular orbital. This is higher energy, electron will go to this one. So, here electrons filling up follow the same principle that was followed for filling up atoms. In atoms, for building up of atoms, electrons are added by following the half-half principle. One has to follow Pauli exclusion principle and Hund's rule of maximum multiplicity. So, using those principles, same principles were used here also to fill up molecular orbital energy levels. So, here is there is one electron, here is another electron, and both electron will go to a level its energy is lower energy, lower. So, both of them will come to this level, that is bonding molecular orbital, they will not go here. Okay. So, the difference between this level and this level, okay, is delta E, that is a bond energy, delta E is a bond energy. Bond energy of two hydrogen atoms, the bond energy of the bond between two hydrogen atoms. So, when two hydrogen atoms are combined, this is the amount of energy released that we have seen in terms of electrostatic potential model, energy model. We have seen that in case of valence bond theory. So, here again the same amount of energy released can be calculated by this way, by molecular orbital method. So, okay, now we can what we have done is combination of atomic orbitals. What are those atomic orbitals? Those atomic orbitals are from different atoms, not from the same atom. In valence bond theory method, atomic orbitals are combined using which are present in the same atom, but in molecular orbital theory, atomic orbitals are combined from different atoms, that is a difference. And then you have molecular orbital energy levels, that is this orbital is called sigma orbital, this orbital is called sigma star orbital to represent antibonding. So, you have a sigma orbital, sigma star orbital, then you have pi orbital, pi star orbital, and then you have delta orbitals. Okay, you can have that, we are not going to see. So, you have like 1s, 2s, 2p, like that. You have sigma, sigma star, pi, pi star molecular orbitals in molecules. So, their energy levels are filled by following Pauli's exclusion principle and Hund's rule of maximum multiplicity. Now, for hydrogen atom formation, so you have combined for this diagram, you have 1s orbital of of one hydrogen atom combined with 1s orbital of another hydrogen atom to give a sigma orbital. This is nucleus, another nucleus, and it is everywhere positive. It is positive. The wave function, sign of the wave function is positive. So, this is called a sigma orbital, which is cylindrically symmetrical. About the internuclear axis. So, this is one combination. Another combination is the phi minus phi b. So, you have your atomic orbital one hydrogen atom minus atomic orbital of another hydrogen atom 1s orbital, and then they give this type of situation. And you have to put the nucleus very close to this border, very close to this border. Okay. So, so that they repel each other. There is no build-up of electron density between two nuclei, between these two nuclei. So, there is a node. Node means a plane where finding the electron is 0. So, this is called node. There is one node. So, compared to bonding, anti-bonding orbitals have one additional node. So, that is what is happening. So, there is no node here, there is one node here. So, node means finding electron in that region is 0. So, nucleus A, nucleus B, they repel each other, then you have to give the sign, this is plus, this is minus, that is the sign of the wave function. So, this is called a sigma star orbital. So, molecular orbital of this one looks like this, molecular orbital of this type looks like this one. Okay. So, because these nuclei repel each other, energy of this orbital is higher. So, that is why higher compared to the contributing parent atoms. So, how much it is decreased, that much is increased. So, total energy remains the same. So, this much decrease in energy, same level increase, that is possible if the two atoms are same. If they are different, it will not be like that. That we will see later, or you will be studying in higher classes. So, what we have seen, formation of sigma orbital, that is bonding molecular orbital, sigma star orbital, that is anti-bonding orbital, by combining 1s orbital. They can be combined in this way. So, this is S plus S, this is S minus S. So, two combination, linear combination, S plus S, S minus S, because two orbitals are, this is one wave function, this is another wave function. They can be combined in a by linear combination method to give this wave function and then this wave function, which are, and the energy levels are like this. Now, you can also combine p orbital to form sigma bonds. So, you have 1s orbital, you have a 2p orbital, let us say 2z pz orbital, 2pz orbital, which can interact with another pz orbital, because its energy level is almost same as this orbital. Okay. So, combination of atomic orbitals is possible only if they have following conditions. For example, for combination of atomic orbital, they should have same or almost they should have equal energy, almost equal energy or same energy, then only they can combine. Another important condition is that they should have same symmetry. Okay. So, 1s orbital can combine with 1s orbital, 1s orbital cannot combine, cannot combine with 2s orbital, because 2s orbital is higher in energy compared to 1s orbital, they cannot combine. So, these two orbital can combine to give a molecular orbital, provided they have same energy or almost equal to each other. But you cannot combine 1s orbital with 2s orbital, because 2s orbital is higher energy. So, when they differ so much, they cannot combine to give molecular orbital. Okay. So, energy should be same. So, energy must be almost equal, Another one is symmetry should be the same. Must be the same. For example, Px can combine with another Px. Px cannot combine, okay, Px cannot combine with Pz orbital. This cannot combine, okay, because symmetry is different, they cannot overlap, because Px is along the x axis, Pz is along the z axis. So, they cannot combine, symmetry is different. So, they cannot combine. So, symmetry must be the same for combination of atomic orbital. Energy must be almost equal for combination of atomic orbital. And then third one is they should overlap very effectively, such that the bonding, okay, the bonding is stronger. So, overlap must be greater. They must to overlap better, otherwise there will be no bond formation, because overlap is related to the bond strength. Higher the overlap, higher the bond strength. So, they must overlap. So, these are the three conditions must be met for combination of the atomic orbital to form molecular orbitals. So, you can combine. So, what we have seen is the combination of 1s orbital with another 1s orbital. Now, we are seeing combination of p orbital with another p orbital. So, if you take Pz orbital as the axis, where the internuclear axis, as the internuclear axis, then you can draw the interaction diagram of this type. So, Pz orbital interacting with the 2 Pz orbital, then you will have one energy level lower in energy, another one higher in energy. So, which are connected by this type of, okay, diagram. So, these dotted lines or solid line you can draw represents the interaction between, okay, these two orbitals. After interaction, two energy levels are formed. So, they can combine each other, because symmetry is same, energies are same, and they can also overlap by head on overlap that we have seen yesterday. So, you can describe the overlap of the Pz orbital in this way. If you take atom A having Pz orbital, this is a nucleus, positive, this is negative, that is sign of the wave function. Combine with another p orbital, this is nucleus, this is positive, negative. So, this is p plus p will give sigma orbital of this type. This is positive, negative, this is negative. So, there is a node, two nodes are here, two nodes are there. So, this is a sigma orbital formed by p orbital. So, sigma orbital, the corresponding anti-bonding orbital is represented in this way. This is p minus p, we will have like this. Like this. So, this is minus plus minus plus, and there are, these are the nodes. So, you can see that compared to sigma orbital, this is sigma star orbital, that is anti-bonding orbital formed by p orbital. So, compared to bonding orbital, in anti-bonding orbital there is one additional node, that is 3 here, here 2 is, so there is one additional node. So, this is a sigma orbital formed by p orbital, anti-bonding orbital sigma star orbital formed by p orbitals. Same way. So, we have seen combination of S plus S, S minus S, P Z minus P Z as well as P Z minus plus, okay, both linear combination of p orbitals, P Z orbitals. Now, what about P X and or P Y? They are almost equal for forming pi bonds. So, Px we have seen Px can combine with another Py, Px or Py or py plus py can give, okay, pi bonds, or py plus py can give pi bonds. Let us see how do they look like. So, if you take this is a px orbital or py orbital, px or py, okay, this is px or py, and then two energy levels are formed, two molecular orbitals are formed. This is atomic orbital of one atom, this is atomic orbital of the another atom, combined to give two molecular orbitals. So, this is a pi bonds which are connected to the parent atoms. This is pi star, like sigma star, you have pi star here. So, this is a pi orbital formed by px or py orbital. How do they look like? If you take, this is the internuclear axis atom A, okay, and this has a px orbital, this plus, this minus px or py, okay, then combining with another atom B, okay, its orbital, px orbital is this one, plus minus, okay, this is a nucleus, this A, this B can give, this is internucleus, this is a nucleus, on top of the nucleus there is a cloud of electron, on top of, below this plane there is another cloud of electron density. So, this is positive, this is negative, so that is a sign of the wave function. So, there is a node along the internuclear axis. If you combine the orbital in the reverse, so this is a px plus px. Now, you take another combination, this is A, this is plus minus px or py minus, okay, nucleus B having a px orbital plus this minus this px orbital can give like this. This is internucleus axis, this is atom nucleus, and then you have like that, there is a like that, you have like that. Now, how many nodes are there? There is a node along the internuclear axis as well as there is a node along the perpendicular to that, perpendicular to the internuclear axis. So, additional node is present there. So, this is called, so this is a plus minus plus minus. So, this is called pi star orbital, this is called pi orbital, okay, contains electron density above the above this plane, above the plane formed by these two atoms, and there is electron density below that plane. Okay. Here you have nucleus, between the nucleus electron densities decrease. So, they repel each other. So, that is why higher in energy, like sigma star orbital, pi star orbital is higher in energy. So, these are the molecular orbital pi, pi star, sigma, sigma star orbitals. Now, from the molecular orbital theory, we can talk about the stability of the molecules. That stability can be judged based on the number of electrons present in the anti-bonding orbitals as well as from the number of electrons present in the anti-bonding orbitals. If you take hydrogen molecule, so you have a hydrogen atom A combining with the hydrogen atom B, and this is a molecular orbital. It has one electron, it has one electron. Both electrons go to the lower energy sigma orbital. This is sigma star orbital. Okay. Now, we can talk about the stability of the hydrogen molecule. We know that it is very stable. How? Because there is a pair of electron between the two hydrogen atom. That pair of electron is located in the sigma orbitals. So, if you consider this as a bonding electrons, so the number of as NB, so the number of electrons in bonding orbital as NB. Similarly, the number of electrons in anti-bonding is taken as NA. Then we can talk about the stability of the molecule by using the concept called bond order. Bond order is the multiplicity of the bonds between atoms. So, bond order is equal to just difference divided by 2. So, a number of electron present in the bonding molecular orbital minus number of electron present in the antibonding molecular orbital divided by 2. So, from this bond order we can talk about the stability of the molecules. The bond order should be positive for stable molecules. So, the B, okay, so this is a bond order. The bond order, okay, should be positive, okay, then only the molecule can be stable, should be positive for stable molecule. If the bond order is 0 or negative, this is unstable. If the bond order equal to 0, molecule is unstable. Molecule is unstable. So, from that we can tell, what we can tell from the molecular orbital, whether the molecule is, we can draw a interaction diagram or molecular orbital diagram of this type, and then we can talk about the stability of the molecule by looking at the number of electron present in the bonding orbital and then number of electron present in the antibonding orbital by using a concept called bond order. The bond order refers to bond order can be 1, okay, bond order can be equal to 1, that means it is a single bond. If it is 2, it is a double bond. If it is 3, it is a triple bond, and so on and so on. So, we can, so higher the bond order, higher the stability of that molecule. Okay. So, then the bond distance, so there is a relationship between the bond order and bond length. Higher the bond order, shorter the bond length. So, when you compare the bond distance between single bond and triple bond, single bond distance is always higher for the same molecule, for the same atoms, higher compared to, or the single bond distance is longer than the double bond distance or triple bond distance. Bond order is higher means multiple bonds. Multiple bond distance are lower compared to single bond distance. Now, for hydrogen molecule, let us calculate the bond order. So, for hydrogen molecule, the bond order equal to number of electron present in the bonding orbital is 2 minus number of electron present in the antibonding orbital 0 divided by 2. Okay, it is just 1/2 of the difference between the number of electron present in the bonding and the antibonding electrons. So, equal to, so 2, okay, 0 equal to 1. So, the bond order for, okay, is 1. So, that is why there is a single bond present between the two hydrogen atoms. So, bond order is 1, the molecule is stable. Okay. So, stable, molecule is stable. Now, let us see another molecule. After hydrogen, you have a helium, whether it is stable or not. Let us see. From the electronic configuration, you have 1s orbital for helium atom is a 1s orbital, which is completely, there are 2 electrons in there. So, another helium atom, you have 1s orbital, it has 2 electrons. So, they interact and form 2 molecular orbitals, which are represented in this way. Okay. Now, this helium atom has 2 electron, similarly this helium atom has 2 electron. So, we have to fill up the molecular orbitals. So, you have to start with start from the lower energy level. So, this is a lower energy level, both electrons. So, because like atomic orbital, molecular orbital can also accommodate only 2 electron, and the spins should be opposite each other, that is Pauli exclusion principle. Same principles are used here. Maximum multiplicity, Pauli exclusion principle. Then another 2 more electron will go to the antibonding orbital. So, this is a bonding sigma orbital, this is antibonding sigma, okay, this is sigma star orbital. So, molecular electronic configuration written sigma 1s orbital containing 2 electrons, sigma star orbital formed by 1s orbital containing 2 electrons, that is a molecular electronic configuration for He2. Now, bond order, if you calculate, bond order equal to number of electron present in the bonding electron 2 minus number of electron present in the antibonding 2 divided by 2 equal to 0. Okay. So, that tells that there is no bond between 2 helium atom. So, helium is unstable, Okay. That means it does not exist, that is true, experimentally found that it does not exist. So, there is no He2 molecule in the world. So, because there is no bond between 2 helium atoms. That is how you can do that. So, this is a molecular electronic configuration. Let us see another molecule. After helium you have lithium, Li2. Let us see whether it is stable or not. So, in lithium electronic configuration is 1s2 2s1. So, we have to combine two atomic orbital, 1s orbital, 2s orbital. So, let us start here. Okay. So, here you have 1s orbital of one helium atom, another 1s orbital of another helium atom, and then you have a molecular orbital formed between them. So, always remember, as you go up, energy is increases. So, energy increases. Then you have 2s orbital, here is a 2s orbital, and there is a sigma bond, there is an anti-bonding orbital, and the interaction is shown as a dotted line. And then we have to, so this is one lithium atom, this is another lithium atom. You have here Li2 molecule formed between them. Now it has 2 electron here, 2 electron here, both will go here, another 2 will go here. Now if you look at that, there is 1 electron here, 1 electron here, there is 1 electron here, then both will go to the bonding molecular orbital. So, this is sigma, sigma star, this is sigma, sigma star. Now, the molecular electronic configuration is sigma orbital formed by 1s orbital containing 2 electron, then sigma star orbital formed by 1s orbital containing 2 electron, and then you have a sigma orbital formed by 2s orbital containing 2 electron only. So, in total 6 electron, because 2 lithium atom is combined, 1 lithium atom 3 electron, in total after Li2 contains 6 electrons. So, 2 plus 2 plus 2 6 electron. The number of electron is the same after forming molecules. Okay. Number of molecular orbitals should be the same after forming molecular orbitals. Now, you can see that how to calculate. Well, now we have to find out whether it is stable or not. Okay. This bonding cancelled by the anti-bonding of this. So, 2 electron cancelled by another 2 electron present in the anti-bonding. Now, here bond order. Okay. So, you have to here you have to work here. Here the number of electron in the bonding is 2 minus number of electron anti-bonding is 0 divided by 2 equal to 1. So, Li there is a bond between 2 lithium atoms. A single bond is formed. So, it is stable. So, that is how we can talk about bonding between atoms as far as molecular orbital theory is concerned. Thank you.